Throughout this chapter, we'll see the noise performance. So noise itself is random in time, so at a certain point, the amplitude vary a lot. So the way we can communicate with others about the noise is just the noise power level, or the standard deviation. If you measure the standard deviation of the noise distribution, it has a zero mean and follows the Gaussian distribution. So Gaussian distribution specified by two things. One is its mean, so typically it's 0, and sigma, the standard deviation. If the standard deviation is large, then you will get larger noise like this. So plus minus 3 sigma region, it covers how much probability? It covers almost 99.7% and covers the population, most of the population. So to properly calculate the standard deviation, how we can do is that we take the square of the voltage and then take the mean of that. So expectation is mean. So expectation of noise voltage square, that would give us the average noise power, right? So this is kind of average noise power that give us the sigma square. So once we find that the sigma, we can represent the noise voltage in RMS. So we represent noise voltage in RMS only. Can you say that noise voltage amplitude is 1 millivolt or 2 millivolt, something like that? No, you cannot do that, because noise is always time varying. But it's a statistic behavior, like power level or variance is kind of defined. So we calculate the voltage in RMS fashion, right? So this is something that you have to remember about the noise. This is more detail about the probability value. So if you consider only plus minus sigma, within the sigma, it contains 68% of the all population. If you take into account plus minus 2 sigma, then 95%, and again plus minus 3 sigma covers like 99.7%. So if you are concerned about, let's say you have a signal xt and noise added onto it, so let's say time varying, so this means that this value will be within that, how much, so we know that the xt plus nt, so this is noise and signal. So nt, noise value can be within that, each amplitude within that, how much, 9 plus minus 3 sigma. We can say that with that within the plus minus 3 sigma, with the probability of 99.7% confidence. This is kind of confidence level. Right, but definitely 0.3% will lies beyond this the level. So the event such case happen is very rare. So typically people consider like a 3 sigma value for the when you design the circuit level. You expect like how many sigma tolerance should be implemented in circuit. In that question, you have to be able to come up with a good solution to work properly even with this kind of a noise distribution. So we just look at, so far we just looked at the plus or minus 3 sigma, but in some application you may want to consider more even tight noise specification, like a plus or minus 4 sigma case, like this is almost 0.99%, 99.99% accuracy. If that is the case, we just cover such large if we consider that plus minus 4 sigma, the noise voltage beyond this range would be very rare. This, so far we just assume that the noise behavior is Gaussian distribution, but in sometimes Gaussian, if you design the circuit properly, then you may see like this kind of a nicely behaved Gaussian distribution. But in some other region, you may see different distribution, like dual mode, like this kind of a noisy distribution or something like that, right? This kind of a case may happen if you in your circuit some history or the two different operating mode, two modes of the operation may result, right, result in like result in non-Gaussian like noise, right? In that case, you have to revisit your circuit and what is causing such kind of behavior, and find out and fix that error, right? Try to minimize such kind of error. That should be done in circuit design level, okay? But typically when you simulate like AC noise simulation, the noise simulation is AC based on noise sim is based on AC small signal analysis, based on the DC analysis or the small signal analysis, the linearized model. So for large signal, behavior is not properly captured, so you may have to change the output voltage level to properly capture the noisy response. For example, your circuit output swing like a sine waveform, right? It may have a near zero, it may have a small noise, but it may have a larger noise at the peak and lower peak, something like that, right? This kind of the different noisy behavior is coming from the large signal behavior. The operating point is actually different from peak to the middle here, right? Q1 and Q2. So for worst case noise simulation, you may have to consider like you may have to consider large signal noise simulation. Okay, so you may have to double check when the output is large, you simulate the noise, or when the output is small, you may simulate the noise like that. Okay, so this is something that you have to consider. If you look at the noise in frequency domain, you will see this kind of a noise spectral density. So expectation of n square mean square noise is like following at low frequency 1 over f noise, meaning it has minus 10 dB per decade slope, and then we have a flat white noise spectrum is there. So this kind of spectrum is observed. So in this kind of case, when you find the noise voltage in RMS, you must define the noise frequency that you care about. Obviously, if you integrate all the noise through the infinite frequency, then you get the infinite amount of power noise. But in reality, the system is bandwidth limited, so you have to care only about the frequency you care. So in this example, let's say we care about the frequency F1 to F2, then total noise power can be RMS noise voltage can be found by finding noise powers, taking integral of the frequency F1 to F2 and frequency density, noise density profile, here dVn square. So this is the dVn square. This is density of the noise power. So that give us what? If that is a white noise level, then we get this F2 minus F1 times dVn square. Right? This is the RMS. If you take the square root for all things, then that gives us the RMS voltage level. So this kind of a noise density is represented in volt square per hertz. So meaning mean square noise per hertz. 1 hertz mean square noise per hertz, right? So within the 1 hertz window, how large the noise power is the noise density. So noise power per hertz. If we know that number, then we can calculate the overall noise voltage in RMS in this mathematics. So from this observation in frequency domain, so let's say we have a device on the test and take some, let's say, low pass filtering signal bandwidth like a PW, and then measure power measure that give us a Vn square. From that we can find out the noise voltage in RMS, right? So one question is, if you increase the noise bandwidth, how large so your noise profile will grow, right? So larger the bandwidth, the noise bandwidth, let's say NBW, let's say call it MBW. MBW noise bandwidth is larger, you get the larger noise voltage in RMS. So you get the larger spectrum, larger sigma Gaussian distribution. So this is kind of a behavior of noise. So it is important to know what is your noise bandwidth. So noise bandwidth is also a critical factor to calculate the RMS noise. When you add three noises from different noise sources, how we calculate the noise level. So in this example, X1 and X2 and X3 are coming from all different sources, meaning all these noises are not correlated. It doesn't have any relationship with the different noise source. So this is independent noise. So when you add them up, it's total output power level. How we get the output power level? So let's say the x1 noise level, this noise level is x sigma RMS sigma 1 and sigma 2 and sigma 3. Then overall noise voltage will be what? So if you that would be total output noise power would be square root the x total noise power would be sigma 1 plus square plus sigma 2 square plus sigma 3 square, like this, because this is the simple equation that you can get out of the random process and statistics mathematics that give us this relationship. So what if we have a sigma 1 and sigma 2 and sigma 3 that are all having same sigma, same power, noise power? In that case, sigma total square would be what? 3 sigma. Let's say this is sigma, 3 sigma square. So in RMS voltage level, that would be square root of 3 times sigma, right? This is the case of the uncorrelated noise sources. What if we have some noise behavior like somehow correlated, meaning each noise behavior, noise waveform is somehow very similar in time? So in that case, if you add them up at the same phase at the maximum peak, you will get the maximum noise voltage. All these noises are added in time, right? So this can be simply calculated. For example, x1t is like a1 and let's say sine omega t. Let's say the noise source has the single noise frequency omega n. Let's say x2t has the, let's say, a2 sine omega nt, and x3 is a3 times sine omega nt. In that case, what is the x total noise power? X total RMS value of noise total. So for each signal, we know that RMS value of this sine waveform would be x1 RMS would be what? A1 over square root 2, right? x2 RMS noise level would be a2 over square root 2. So x3 RMS would be a3 over square root 2. For total noise, RMS value would be just simply x1 plus x2 plus x3, right? So that gives us a1 plus a2 plus all these amplitudes are added on top. So finally, x total RMS value would be what? a1 plus a2 plus a3 over square root of 2, right? So uncorrelated and correlated case, mathematics are totally different. So for the random noise, we assume that basically uncorrelated noise source and all those noises are independent, right? Based on that assumption, when you add them all of the noise, we can calculate the total noise power or noise RMS value here. Can be found like that. Okay. Signal to noise ratio can be defined once we know the signal power and noise power. For the sinusoidal input like this, through the amplifier, we amplify the output and the circuit noise like this. So SNR can be defined by the signal power over P noise, and the, let's say for example, for simple example, if the output, our signal ST is, let's say, A sine omega t, our signal frequency at omega 0, and the noise power NT. Noise is something random in behavior, right? So we cannot write down each equation. Only we can say that variance, standard deviation of the noise, that would be sigma n, right? In that case, so SNR can be defined by the amplitude A, the signal power would be A squared over 2, and divided by power noise would be sigma n squared. So this is something that you can find. Now the question is how we find that the sigma n noise standard deviation or RMS value, sigma RMS. That can be if you know that the, let's say, amplifier noise bandwidth amplifier is passing through like this frequency up to 1 megahertz, for example, we can integrate all these noise sources through this amplifier, right? So through that bandwidth, then that gives us what? Integration of whole things would be n, sigma n squared, right? Our signal, it may be single tone sine wave form or multi-tone or various signal tone, right? All these signal power can be calculated P6, right? Usually we can specify the maximum signal, maximum SNR. For in this case, you would calculate the maximum signal swing you find through the amplifier and take the power level. You know that for the given amplifier, no matter what the frequency is, output signal range is quite limited, right? So once we know the maximum signal swing, then we can calculate the maximum signal power easily. So that would be like that, A squared over, that would be A max over 2, right? Obviously, if you limit your bandwidth, you will get the lower noise power, but also you will have the less signal bandwidth. There is some trade-off between the amplifier bandwidth and the noise power, right? Now let's take a look at the electrical component and noise description. For example, we have a resistor here. It has some noise behavior through this device. How we model is that we model that, as I say, noisy resistor can be modeled with the noiseless resistor plus noise, right? Here, noise voltage, if you measure that, that is kind of this, that is in frequency, it has a unique feature. For example, noise spectral density shown in here is one-sided noise spectral density. If you specify that in double-sided, then positive and negative frequency here, that would be half of that, so 2 kT RHD noise density, double-sided. For the one-sided, we have a left and right symmetry in double-sided. So if you have a one-sided, then you have a 2x larger noise density here. So 2kTR is noise power. If you have a larger R, you get the larger noise density. Lower R, you get the lower noise density. As you are getting larger, and you get the higher noise floor. This is measured in voltage output. So you can have you can model the noise register with the voltage, series voltage model is one way. The other equivalent method is putting parallel noise current source like that. In that case, we can easily find that equivalent noise density, current density, right? Current noise density can be found from here to note from Norton and Thevenin equivalent model. You can easily move back and forth to different model. These are equivalent, those two model. That would be the R voltage scale over R scale. That would be 4kT over R is the noise density. Here we have a different notation here. We had like a DF here, so meaning we are having this number for KTR is like a noise density, spectral density. So when you want to measure the actual noise RMS power, you have to multiply by noise bandwidth, right? MBW. So if you know the noise bandwidth, then we can find the final RMS noise voltage here. In that way, we specify like DF in here. So there are two different ways of representing noise in textbook. So Rajabi's textbook, they are using this convention. Just specify the noise density. And Sanson's book, we have this kind of a noise density equation. Sometimes people or students are confused with this kind of a notation, because that is not noise power itself, it is just a noise power density. So this is density, spectral density. So from that, if you want to calculate the RMS value, we need the frequency of interest. If we have that, then we can calculate the RMS value, right? So with that information, okay. For example, for 1 kilo ohm resistor, how large is the noise spectral density? That would be 4 nanovolt RMS per square root hertz, right? At temperature, room temperature, right? So once we know that, for the signal bandwidth like a 1 megahertz, then you know that how large the noise voltage is. For let's say NBW, let's say 1 megahertz, then our 1 kilo ohm results in how many voltage? So 4 nanovolt square times 10 to the power of 6 and square root, right? That gives us what? 4 nanovolt times 10 to the power of 3, right? That gives us what? 4 microvolt, right? RMS. This is a hertz. Nanovolt per hertz, right? Nanovolt for root to hertz. You need to be careful about the unit. So right. Okay, this is something that how you calculate the noise voltage, right? Here. let's take into account the low pass filter shown in here. So we only have the noisy source resistor here. The capacitor is noiseless, it doesn't have any noise, but when you have a resistor connected to it, then we see that output noise voltage across the capacitor. So let's calculate how large the noise is measured in here. So we know that the resistor noise spectral density in voltage is 4 kTRS. So its transfer function is low pass filter given by this bandwidth like 1 over 2 pi RS CL. So if for the input like a noise voltage shown in here, you will go through this kind of RC transfer curve. So we have to find the integral of all the noise through this bandwidth. So how we get that? So we have the spectral density power integral times this overall spectral transfer function is that 1 over 1 plus f f 2 pi j 2 pi f over bandwidth, right? For this case, the noise power would be what? 0 to infinity dVr skew expectation over times HHF absolute and square, right? That would give us that equation, right? So we have to calculate this equation 1, that is shown on the right here, on the right at top. So this special, we know that there's a special integral function. Each value is pi over 2. From 0 to infinity is dx over 1 plus x squared is pi over 2. Using this fact that we can simply calculate the overall integral value, we have this is a constant, so 4 kTr, and so that would be bandwidth times pi over 2. So this equivalent noise bandwidth would be the circuit bandwidth times 2 pi over 2 times, right? So this is a simple way to calculate the noise power using the fact that they shown on the right. So plug that into this equation and you will get the overall noise would be what? So bandwidth is what? 1 over 2 pi RS CL. So we have RS cancelled out, pi cancelled out, and we have a 4 cancelled out. So as a result, this is df not shown here because we already take into account the overall frequency. So overall result will be KT over CL. So this is the power noise voltage. So RMS value would be KT over CL. Take the square root of that. So for example, for 10 picofarad, that results in 21 microvolt RMS. For 1 picofarad, we have a 65 microvolt RMS. So what's surprising is that in this equation, no R specified here. So no matter what the R is the Output noise voltage is governed by, in RMS, is determined by what? By CL, right? Output load capacitor. So this is called KT over C noise. So if you have a larger register, you will get the larger noise level and smaller bandwidth. If you get the smaller register, you get the larger bandwidth but lower spectral density. But what happened here is that if you integrate everything here, the overall power is the same no matter what the R is. So this is a very special feature out of a simple RC network. So only the capacitor size can control the amount of noise level, but the noise itself coming out of the register, not from the CL capacitor, but the actual noise magnitude or RMS value can be set by the capacitor. This is a very important fact that you have to understand for the integrated noise level of the register. Okay. So far we just looked at the white noise level out of a register, but in register itself, it also have the flicker noise following minus 10 dB per decade slope. So if you add them, if you extrapolate those two, the overall power would be larger, slightly larger like this. So following like this, and if you add them up like this, here the maximum deviation would be what? If you add the same noise power level, then how large is the difference? The difference would be 3 dB, right? It adds in dB in 3 dB. So if you in power, you get the 2x larger power level. So this can be formulated by some factor, proportional factor divided by F. So typical 1 kilo ohm resistor, we can find that the flicker noise level, but the flicker behavior is somewhat different from this thermal noise level. Its behavior is slow random motion. So if you have a larger device area, we get the lower flicker noise. This is something that physical behavior was observed. So for the same poly register, like a register like here, if you for the, let's say, W and L here, if you draw much larger, let's say 2W and let's say 2L, for this kind of register implementation, you are having the same R, but here less flicker noise. The flicker noise is reduced by the larger area. And another way of reducing flicker noise is that removing DC voltage or currents. So by passing through the capacitor like that, so there's no DC current flow, and then we can get the smaller flicker noise. This kind of technique also can be used in a transistor, like a switch level. Transistor also has noise, flicker noise, much larger flicker noise than resistor. In that case, we cut down the DC current or voltage across the drain and source, then we can get a smaller So larger area or removing DC biasing results in less flicker noise. So we get the lower and lower flicker like this, right? By having larger area. Typically, the register has very low flicker noise, so we usually ignore that register flicker noise. The register has very low flicker noise, 1 over F noise. So open time we ignore. Okay. Let's do some exercise for calculating noise spectral density. So for the register shown in here, this is a noisy register, right? R1 and R2. For a simple model, we can consider two cases. One is a voltage noise model, so VN1 and VN2. Measuring the VN total. But if shown in here, having this kind of electrical network is difficult, more complicated to find the output noise voltage. In that case, we may consider the different noise equation using the Norton equivalent circuit like this, IN1, IN2. In this case, R1 and R2 are noiseless, right? All the noise are lumped onto this noise voltage source, right? Similarly, here in current source noise model, like that, the total VN total scale. How we get that? So we can easily find that what R1 and R2, we move that noise, two noise sources, N1 and 2, like this, right? Then we can add them up easily because this is the current source. We can add that only one. So its noise power is what? And all those are independent source, so we can add them up. Scale, right? Like this. So now finally, if we end scale, total will be R1 in parallel with R2 total register. Through that, the current noise currents are flowing through this register. So no, the current would be, we have to do the scale because we are looking at the scale of the voltage. So if we go IR, so I scale total scale, that would be R1, R2, IN1 scale, N2 scale, and then R1 parallel R2. What is I1 and IN1 scale? That will be 4kT over R1. The other one is the 4kT over R2. This is again noise power spectral density. Noise density in current. Noise current density. So overall output noise voltage can be calculated like this. Okay. This is a summary. So IN scale total noise voltage can be lumped onto like this: 4kT 1 over R1 plus 1 over R2. Then the overall output noise voltage would be register scale times total noise current, right? So total noise current would be, that is what? 4kT over 4kT times 4kT times over R1 parallel R2, right? So from equation 1 and 2, we can get the final equation 4kT times R1 parallel R2, right? So this notation is again noise power spectral density. So this noise is in 1 Hz bandwidth only. So we were able to do this mathematics using the assumption of uncorrelated noise current. And each noise currents are squared and added, right? Total. And then do the power addition, just simple addition there, right? I total, which IN1 square plus IN2, like this. So we use that equation, okay? Diode also has the noise in it. So diode noise is, we have the PN junction. Any carrier across the PN junction will have a shot noise. So shot noise behavior is what? Only proportional to current. 2QID is the spectral density of the noise current. So for example, for ID equal 50 microamp, then we have a 4 picoamp RMS per square root of a hertz. Right? So this kind of a PN junction creates the shot noise. So movement of carrier is random. This equation can be applied both in forward or reverse biased diode. This is the white noise, so meaning white spectral density is white over frequency. So this is 2QID, right? ID IN square, right? That this level is 2QID. So this is white, but this is different from thermal noise that we were seeing in the register. So we have to add additional factor, coming out of this shot noise. Okay, any diode presented in the circuit will create this kind of a shot noise. Okay.